Assalamu alaikum. In this lecture, I will start with highlighting the pose and the zero in the z plane, and I will start with letting x of z is given as b of 0 z to the power m plus b1 z to the power m minus 1 until I'm having the constant bm over z to the power n plus a1 zn minus 1 until I'm reaching an. And I will assume that this rational function or transfer function is proper, which means that the degree of the numerator is less than or equal to the degree of the denominator. So simply this can be written as n of z over d of z. Now we can write x of z in terms of multiplication of the zeros and the poles, such that certain gain z minus z1 multiplied by z minus z2 until I'm having z minus zm. Here I'm assuming that I'm having m zeros over z minus p1 multiplied by z minus p2 until I'm reaching z minus pn, where here the p's the p's where I equal 1, 2 until n are the poles of x of z. And the zeros where I equal 1, 2 until m are the zeros of x of z. Are the zeros of x of z. Now sometime we are writing x of z in terms of z minus 1, the unit delay. So simply if we multiply x of z here by z minus n over z minus n in both sides, of course, then we can write x of z as a function of the unit delay of 0 minus 1 as b of 0 z of minus n minus m plus b1 z of minus n minus m plus 1 until I'm reaching the last term, which will be bm z of minus n over now here 1 plus a1 z minus 1 plus a2 z of minus 2 until I'm reaching the last term, which will be an z of minus n. Now simply where here z of minus 1 is the unit delay operator. So to find the 0 and the pause of x of z, which better to use x of z in term of z or in term of z minus 1? So to answer this, let's solve the following example. Let's assume that we need to find the pause and the 0 for x of z equal to z square plus 0.5 z over z square plus 3z plus 2. Now simply someone will say that x of z can be written as z plus 0.5 over, and simply if we factorize the denominator here, it will be the z plus 1 multiplied by z plus 2. So simply now x of z has pause at z minus 1 and z minus 2. Simply, in order to find the pause, x of z will equal to n of z over d of z. The solution of d of z equal to 0 will decide the pause of x of z. So simply here z plus 1 multiplied by z plus 2 equal to 0. So simply we have two poles at z equal to minus 1 and z equal to minus 2. Now if we need to find the zeros, then n of z equal to 0 will decide or will locate the zeros of x of z, and simply here in this example we have z multiplied by z plus 0.5, which will give z equal to 0 and z equal to minus 0.5. So simply here we have two poles. One is located on the unit circle, the second one is located outside the unit circle. So simply from our first lecture, the relation between the s-plane and the z-plane, the system will be unstable. Why? Because one of the root is located outside the unit circle. One is located here at minus 2, and the second one is located here at minus 1. And this system has two zeros. So finding the pause and the zero is something very simple. Now what about if we rewrite x of z in terms of the z minus 1? So now let's assume that simply if I multiply by z minus 2, I can get x of z, which now written in terms of z minus 1. It will be 1 plus 0.5 z minus 1 over 1 plus 3 z minus 1 plus 2 z minus 2. And simply this can be written as 1 plus 0.5 z minus 1 for the n of z, and I can factorize the denominator, the d of z, as 1 plus z minus 1 multiplied by 1 plus 2 z minus 1. So now if we assume that this will be n of z and this will be the d of z, so the solution for the d of z equal to 0 will provide us with the same information, that we have two poles, one at z equal to minus 1 and the second one at z equal to minus 2. So here we don't have any problem with the poles. We can locate the poles either using x of z or x of z in terms of z or in terms of z minus 1. Now what about the zeros? Here if we solve the numerator, which is n of z equal to 0, we are getting 1 plus 0.5 z minus 1 equal to 0, which will give us only one root at minus 0.5. So simply this means that the second zeros, or the second zero, which is z equal to 0, is not explicitly shown. So z equal to 0, which is the actual 0, is not explicitly shown. So in finding the zeros and the poles of x of z must be written in terms of z, not of z minus 1. So here we can write a note. In finding the zeros and poles of x of z, then x of z must be written in terms of z. Not z minus 1. So now let's discuss the solution of a difference equation. Let's assume that we have the following sequence. Example here. Let's assume that we have m of k, which will equal e of k minus e of k minus 1 minus m of k minus 1, where k is greater than or equal to 0, where e of k is defined as 1 when k is even and 0 when k odd. And we need to find a solution for the difference equation. So to find the solution for the difference equation, someone will say that we can use the sequential procedure. So one method is using the sequential procedure. So simply we'll start with k equal to 0 and say that m of 0 will equal to e of 0 minus e of minus 1 minus m of minus 1. And simply, by definition of the causal system and by assumption, any negative index will go to 0. And here we'll end up with e of 0, and e of 0 is k now is even, so m of 0 will equal to 1. So we can proceed to calculate m of 1, which will equal e of 1 minus e of 0 minus m of 0. Now here, e of 1, by the definition of e of k, will equal to 0. Now k is odd, minus e of 0, which is the 1, minus m of 0, now which is already we calculated here, so minus 1, and the answer will be minus 2. We can also proceed by calculating m2, which will equal to e of 2 minus e of 1 minus m of 1. Now e of 2 is equal to 1 even minus 0 minus minus 2, so this would be plus 2, so the answer would be 3. We can also proceed by calculating m3, and that's why we call it sequential procedure. So m of 3 will equal to what? It will equal e of 3 minus e of 2 minus m of 2, which will equal to 0 minus 1 minus 3, which will equal to minus 4. Let's assume I'm calculating until m4, and this will be equal to e4 minus e of 3 minus m of 3, which will equal, now 4 is even, so it will be 1, minus 3 is odd, so this will be 0, minus m3 minus 4 minus the minus, so this would be plus 4, so this will be the 5. So we can continue until certain k, and this is what we call the sequential procedure. Now also we can use the Z transform in order to find the solution for the difference equation. How we can do that? So simply here we can use the Z transform to find the solution. So we can use the Z transform to find the solution. So if we use the Z transform, m of z will equal to e of z minus ek minus 1, which is according to the shifting theorem. This will be z minus 1 e of z, and this will be minus z minus 1 of z. If we do separation of variable, we can write m of z equal to z minus 1 over z plus 1 e of z. Now we need to evaluate e of z from e of k. Now remember, e of k was equal to 1 when k is even and 0 when k is odd. So simply, this implies that if we need to find the z transform for e of k, it will equal to 1 plus z minus 2 plus z minus 4 and so on. So e of z, which will equal 1 plus z minus 2 plus z minus 4 and so on. If we multiply here by z to the power 2, we will get z to the power 2 e of z will equal to z square plus 1 plus z minus 2 plus z minus 4 and so on. Now this one actually is e of z. So now this can be written as z square plus e of z. So e of z will equal to z square over z square minus 1. Now, if you remember, this is the relation between m of z and e of z. Z minus 1 over z plus 1 multiplied by e of z. So remember that m of z was equal to z minus 1 over z plus 1 e of z, and now we have e of z. So m of z will equal to z minus 1 over z plus 1 multiplied by z square. Z square minus 1 can be written as z minus 1 multiplied by z plus 1. So z minus 1 will eat the z minus 1, and we will end up with z square over z square plus 2z plus 1. So now we have m of z in term of z. In order to find the solution for the difference equation, we can expand m of z into a power series by long division. So if we expand m of z into power series, by long division, so let's do the long division here. we'll divide z square over the z square plus 2z plus 1. So the first thing here will have the 1, and this will be z square plus 2z plus 1. Subtraction, this will be minus 2z minus 1. Here, if we need 2z, this will be minus 2z minus 1. And we are getting minus 2z minus 4 minus 2z minus 1. Subtraction, this will be 3 plus 2z minus 1. So in order to have 3 here, we'll multiply by plus 3z minus 2, and this will generate 3 plus 6z minus 1 plus 3z minus 2. By subtraction, we will have minus 4z minus 1 minus 3z minus 2, and we can continue. So if I need to terminate this term, I will add here minus 4z minus 3. So now m of z can be factorized into 1 minus 2z minus 1 plus 3z minus 2 minus 4z minus 3, and so on. Now from the definition of m of z, or the z transform, from the definition of the z transform, which can be written as a summation from k equal to 0 up to infinity, m of k z of minus k. So from here we can locate m of 0 to be 1. So this actually is m of 0. This will be m of 1, and so on. And m of 1 will equal to 2 m of 2, minus 2. And m of 2 will equal to 3, and m of 3 will equal to minus 4. Now if we compare this one, this solution with the sequential procedure, 1, minus 2, 3, and minus 4, it will be the same, 1, minus 2, 3, and minus 4.